Wow. So, hi everyone. Welcome to another AI talk, but this time it's different, I swear, or I promise, because this time it's on-device AI. So, my name is Nico. I'm a front-end developer from Switzerland. I currently work for IT, where we provide digital finance solutions, mainly for one client, Berner Kantonalbank, which is a mid-size bank in the canton of Bern, where I live. I'm also part of the Google Developer Experts program in two categories, in web technologies and also in machine learning and AI, which basically just means that I spend way too much of my free time just playing around with all kinds of new web APIs and capabilities that are around the web and AI. And I also like to talk about those. So in the last couple of years, I gave quite a lot of talks. Most of them, almost all of them, were in English, handful in German, but only 2 talks I ever gave were in Berndeutsch, which is my local Swiss-German dialect. Now in September 2021, I had my very first talk in Berndeutsch, and luckily that one was recorded, so I'm able to show you a short clip of how that went. Im Endeffekt, und schlussendlich, im Endeffekt, wird im Endeffekt, ist im Endeffekt, wird im Endeffekt, nur im Endeffekt, wird im Endeffekt, schlussendlich, im Endeffekt, im Endeffekt, schlussendlich, wird im Endeffekt, schlussendlich, Yeah, that's funny. But I'm not joking. That was a 30 minutes talk, and I managed to use the words im Endeffekt and schlussendlich over 35 times. And that was extremely annoying to me when I've seen the video afterwards. Both words basically mean the same. They're like finally or in the end. So it's just like classic fill-in words. So in February 2023, my second talk at Berndeutsch was just around the corner. And I was looking for a way to solve that problem. I was looking for a way to detect those words when I'm speaking. There are solutions in the browser. There's, for example, the Web Speech API, which works great in English and also in German, but certainly not in Berndeutsch. But then again, those APIs, they are just using machine learning models, right? And can't we use them directly in the browser? Spoiler alert, yes, we can. There's a tool called TensorFlow. It was released in 2015 by Google. It's an end-to-end open source framework to use models, to train models, and also to adjust models to your own needs. It was originally written in Python, but since 2019, there's also TensorFlow.js. So we are able to use TensorFlow models and train TensorFlow models directly in the browser or in Node.js. Now, all those machine learning frameworks, they have one thing in common. They require quite complex mathematical operations. And in the case of TensorFlow.js, those are outsourced into so-called TensorFlow backends. So there's, for example, a CPU backend where those calculations are happening directly in JavaScript, which is quite slow. There's a WebAssembly backend, which is a bit faster. But if we want to have really performant machine learning operations, we need to use the GPU. There are some ways to use the GPU on the web. There's WebGL, which is this graphical abstraction layer on top of the GPU. So you have this graphical language that would then do the calculations on the GPU. It is okay, it's way faster than WebAssembly, but it's still not ideal. And since Chrome 1.13 and also Chrome on Android 1.21, there is a new API called the WebGPU API, which is basically an abstraction layer on top of the modern GPU APIs like the DX12, the Vulkan, and the Metal. So we are able, or in this case TensorFlow.js was able to create the WebGPU backend where those calculations are happening directly on the GPU. Now, it always depends on the model and also the device you're using, but in general, WebGPU is almost twice as fast as WebGL. Now, to have a little bit of an example here as well, by the way, my slides, they will be online right after the talk, so you will have all the code and all the links to all the repositories there as well. But what we have here is a quite simple phase landmarks detection model. I can just import that directly from TensorFlow models. I can then create a detector, and I can then pass any image data. In this case, it's a reference to an image element, but it could also be just an image blob. I could just pass that to this estimate faces method, and it will then return an array of faces and also all the key points that it finds in the face. So what I could do then is I can create this canvas, which is on top of my face. I can then go through all the faces, go through all the key points, draw the key points onto the canvas, and I will then have this little mesh on top of my face. Let's have a look at an example. I created this little demo application some time ago, and the idea here is that I will take the current frame from the video input. I will analyze the faces, I will analyze the key points, draw the key points onto the canvas, and I will then take the next current frame. And one thing you can see is that it's super slow. We are now here at about 5 frames per second. And that's because we are using the CPU backend. Let's switch to WebGL. Now we are at 13 frames per second. It's better. But if we then switch to WebGPU, we are now at around 30 frames per second. So it's almost instant face recognition directly in the browser via WebGPU. Now, I released the application on May the 4th, which is International Star Wars Day. So my idea here was to just draw some 2D images on top of my face. So I will take 2 points between the eyes to have the position of the image and also the size of the image. And I can then just draw Jango Fett or also Darth Vader. And I mean, it is a silly application, but in the end, it's a great way to showcase the power of WebGPU compared to things like CPU. Now, since all of that is running in JavaScript, is running in the browser, this also allowed me to create a Chrome extension. So my idea was to just have one, or just be able to control any website just with my fingers. So I can now go to nico.dev, but it could be any website. I can then activate the extension, and I can then use my fingers. Now you can see the cursor that hovers over my website, and I can use that now to do the pinch gesture and interact with the site. I can also click on links. There we go. And that's all done with just JavaScript, and you can see here the webcam. So it analyzes my hand gestures. It analyzes it finds the tip of my index finger and also the tip of my thumb, and it will then take the distance between those fingers to determine the size of the circle. So it sees when I do the pinch gesture. There we go. And one thing you can also see is that the center of the circle is not really the center between my fingers, and that is intentionally because I figured out that when I do the pinch gesture, I move my index finger more than my thumb, so I had to move the center a little bit closer to the thumb to have a good feeling. So that's stuff that we can do with just a couple of lines of JavaScript right now. But there is a small problem with all machine learning frameworks that we have on the moment in the web. Let's take TensorFlow.js. TensorFlow.js, they need to create and also maintain multiple backends. So we have the CPU backend, the GPU backend, the WebGL backend, and so on and so forth. Then I, as a developer, I then need to decide which backend I should use for my users, or should I have some feature detection to have fallback, like if WebGPU is available, then I can is not available, I can fall back to WebGL. If that's not available, I can fall back to WebAssembly, and so on and so forth. It is possible, but it just makes everything more complex. And I told you, I told you that GPU is the most performant way to run those machine learning calculations, and that is true for most devices. But with the rise of AI, we have already seen AI-optimized hardware. For example, my Pixel phone has the TPU, which is the tensor processing unit. There are Windows is working together with Qualcomm to have those Copilot Plus laptops, and they ship with an NPU, the neural processing unit. And it doesn't make sense for the browser to have like web NPU APIs and web TPU APIs. So there is a new proposal that people are working on right now, which is the Web Neural Network API. So in the end, WebNN is then just a standard that provides a high-level interface for running neural networks in the most performant way for each device. So as you can see here, the way we would use that would be that we have our models, the Onyx models, TensorFlow models, other models. Then we have the frameworks that right now have to provide all those adapters. With WebNN, they don't need to decide whether to use GPU or WebAssembly or WebGL. They can just use WebNN. WebNN will then consume the native operating system APIs like these ML Compute or DirectML, and those operating system APIs, they will then decide whether they can access the CPU, the GPU, or they need to fall back to the CPU, and so on and so forth. So that means we could have AI-optimized hardware to run our models in the browser. So let's get back to my original use case. Because the thing I wanted to achieve is I wanted to detect my words when I'm speaking, right? The thing is, words are not images. We have seen a lot of image processing, except when they are, because every word, every piece of audio can be converted to a spectrogram, and we can then create a model for X times me saying just one word. I can then take that model to compare it with the spectrogram of my whole talk, for example. There's also a tool by, or a library by TensorFlow.js. There is the speech commands model. And by default, it will just look for some of the default words like 0, 1, 2, 3, and so on and so forth. Of course, my Swiss German words, they are not in that list. So what I had to do is I had to train my own model. And there is a tool that helps you with that. It's called Teachable Machine. And what you see there on the right-hand side is that's a screenshot from Teachable Machine. And Teachable Machine allows me to create my own classification models for visual or audio input. So what you see there on the right-hand side, on the top, there's this background noise class, which is just me for 1 hour just talking. And then I have two classes, schlussendlich, which is 50 times me saying schlussendlich, and im Endeffekt, which is 70 times me saying im Endeffekt. And I can then train everything happening all directly in the browser, so no data will leave the client at any point. And I can then train that. It will return this model.json and the metadata.json, so two files that I can then pass to this recognizer function. And when it runs now, it will now look for the words that I specified. Now, since my slides are running in the browser, and the browser obviously understands JavaScript, I was able to create a little extension for my slides. There we go. So I can now activate that, and it will now listen to everything I say. And whenever I say im Endeffekt, it will trigger the buzzer. And I actually did use this extension in my second talk in Swiss German, and it did work. So I did use those words from time to time. But I was very cautious of when or why did I use it, because it was a little bit annoying in the end. But now, having this newly trained model, as you've seen, it's quite easy to create the model that will look for certain words. So wouldn't it be also possible to have a model that could transcribe a whole talk? Well, there are models that are specified exactly for that. There's, for example, the Whisper family, which is a family of transformer models that were trained and then open sourced by OpenAI. And with those Whisper models, we can actually pass any audio and it will transcribe the audio. The way we can use that in the web is with Transformers.js. Transformers.js was released in 2021 by Joshua Lochner, and he's better known by his handle Zenova. And he then joined Hugging Face in 2023, so the whole project is now part of the whole Hugging Face family, so it's pretty stable and we can expect it to be around for the next years. And the cool thing is, it was designed to be very close to the Transformers Python library, so if you are already familiar with machine learning in Python, it's quite easy to try Transformers.js as well. And the way it works under the hood is that it takes this Open Neural Network Exchange standard, which is an open standard for machine learning models, and it takes this Onyx runtime. And the Onyx runtime is a project maintained by Microsoft, which basically allows us to compile any Onyx model to different devices. So there's the Onyx runtime web, where we can compile a Onyx model to a web-compatible runtime. It's a WASM runtime, which will then use WebGL, or since a couple of weeks there also the Onyx runtime web that also supports the WebGPU. So the way we can use it is that we have this pipeline operator. We can import that from Transformers.js. We can then create this transcriber where we first have to specify a task. So in our case, it's the automatic speech recognition task. We can then also pass a model. In that case, we want to have this Whisper Tiny, which is the smallest model from the Whisper family, which is hosted on huggingface.co under the Zenova namespace. And I can then pass basically any audio to this transcriber. I can then define a language, which is English, and it will then return an output or an array of output interfaces that I can then join. So I have my my string of what I said. Now, the thing that I wanted to achieve is real-time transcription. And there's one big problem with real-time transcription, and it's pretty hard to know when to send which part of the recorded audio to the transcriber to have, first of all, a meaningful output, because when I send every 5 milliseconds, it will just have those bits without any context, so the captions would be really bad. But it should still feel real time, means that we can't wait for 5 seconds, then send those 5 seconds to the transcriber and then to display those 5 seconds. So it should have meaningful output and also be real time. And I then stumbled upon a project by Zenova, and he used real-time captions as an example for the new WebGPU implementation from Transformers.js. And the way he solved it is pretty cool, because he split it up in 2 basic tasks. On the one hand, you have the media recorder, which is just recording, and whenever it has data, it would add the data to a queue, which is just an array of audio data. And on the other hand, we have our transcriber, which is a web worker that will just run whenever it's ready. It will run again, so it will indefinitely just run, and it will transcribe the whole queue, and to then set the text from the whole queue as our output. The only problem is that when we run the recorder for a couple of seconds or even minutes, it will just grow and grow and grow, so it will be always harder or takes longer to transcribe. And the way he solved it is that he would just cut the audio after a couple of seconds, so you only have the latest 5-6 seconds that will be transcribed by the transcriber, which works. It's not the worst idea, but I wanted to try a different approach. So I created my own little application, which instead of cutting the audio after a couple of seconds, I would just wait for pauses. Means that whenever the transcriber returns the same text twice, I know that there was a pause because there wasn't more to add to the string. And I also knew that it's pretty certain that this piece of text is done, is finished, is ready, and he will then take the string of text, move that to an archive, empty the queue, and then start all over again. Now you can go to captions.nico.dev to try it out, but again, since my slides are running in the browser, I was able to create another little slides extension. And by the way, I did not know that we would have real-time captions for here as well. So it will be fun to see maybe which one is better. So yeah, so it will now listening to everything I say, and it will transcribe that. And what you can also see is that it tries to improve. So it will have those very small bits, and it will then try to improve that. And yeah, I mean, it works. Am I faster? Yes. And by the way, it's all open source. The model is open source. My implementation is open source. Transformers.js is open source. I think that's pretty cool. It was? Okay. Now, being able to run those models in the browser is cool, is fun. But then again, those models, everything I showed you is just pattern recognition. And pattern recognition is cool, but it's so 2019. I mean, nowadays, everyone is talking about generative AI, about LLMs, which begs the question, can we run LLMs in the browser? Well, we do have WebGPU, we do have WebAssembly, we do have all the bits that we need to piece together. So the real question should be, what does it take to run LLMs in the browser? What problems do we have to solve? First of all, the way most of us use LLMs right now is basically like that. We have an input string, write an essay about the GPU. We will send that just to some kind of LLM cloud provider, and they will then return the output, and we're done. That's cool. If we want to run those on the browser, on the device, we need to dig a little bit deeper into what is happening inside this black box there. So first of all, LLMs, machine learning models, they don't work with text or with images. They always need numerical input. So the first thing we need to do is we need to split up our input string to tokens. So tokens are just parts of words in the end. And we can then map those tokens to their numerical representation. So we have just a list of numbers that we can send to the LLM. And on the other hand, we will get a list of numbers back. We can then map those numbers to their tokens, concatenate those tokens, and then we have our text. But what's exactly happening between those processes? There's a lot of magic going on, right? Well, one thing I want you to take home from that talk is there is no magic in AI. There is no magic in machine learning. Everything comes down to just math, numbers, and artificial neural networks. Of course, that is a very, very simplified example of an artificial neural network, but in the end, we do have neurons, we do have layers of neurons, and we do have their connections, we do have the weights between those neurons. And that's the same thing for a simple pattern recognition or also for an LLM. We do have those weights, we do have the neurons, and we do have the layers of neurons. We can split that up into two different sections. We have the architecture, which defines how those calculations are going through the network, and we have the weights. And the weights are the reason why those LLMs are as big as they are, because when we take the Llama 2, for example, which is an open source LLM by Meta, there we have a 70 billion parameter model, means we have 70 billion weights, 70 billion numbers that we need to store somehow. And if they are stored in 16-bit floats, means we end up having around 140 gigabytes of just numbers that we need to process. And that's a lot. That's too much to run in the browser. There are smaller models. There's, for example, the Gemma 2 and the Gemma 2B, which is an open source LLM by Google. It's like the small brother of the Gemini models. And that's a 2 billion parameter model. Those are stored in 32-bit floats, so we end up having around 30 gigabytes of data, which is still a lot. But there's also a process called quantization. And with quantization, the idea is that instead of using 16 or 32-bit floats, we will only use 4 bits per number. So we will have 4 bits per weight, so we end up having around 1.4 gigabyte. And yes, those numbers are less precise than 6 and 32-bit floats, but they are still precise enough for most LLMs. On the architecture side, There are a couple of projects that try to bring those architectures to the web. There is Keras that is used by TensorFlow and MediaPipe. There is Onyx that is used by Transformers.js, as you have seen before. And there is Apache TVM, which has this machine learning compile stack, and that's also the tool that I use to compile my LLMs to the browser. And what we have here is this machine learning compiler allows me to compile a model to a WebAssembly binary, and I can then use this to, or it will then use WebGPU under the hood to do those calculations. I have the weights, which are stored in shards by 30 megabytes per file, and I do have the tokenizer, so I end up having around 13 megabytes for the tokenizer, 1.8 megabytes for the runtime, and then those 1.4 gigabytes for the weights. So it's a lot, but we can work with that. There's also a library that you can use, which is called WebLLM. It's made by the same people that also work in the Apache TVM ecosystem. Here we can create an engine using the ID of the model that we want to use, and then we have a very similar API it's very similar to the OpenAI API, where we can just pass messages. We can also pass a whole conversation to give the model the whole context, and it will then return the whole message. In my case, I wanted to use the Gemma 2B, and we can also use our own models. There is this compiler, it's a Python library that allows us to compile the model to this MLC standard. I can then add my model to the model list, so it's hosted somewhere on my website. Then I have the link to where the model is hosted. I have the URL where the WebAssembly binary is hosted, and I have my unique ID, which is Nico's Gemma 2B ID, and I then need to define the ID as the first parameter, and then I can use my own model. In that case, it's just the classic Gemma 2, but I could also use a fine-tuned version of Gemma 2 for my application. So let's have a look at some examples. MDEdit is a tool that I've built a couple of months or even years ago. And originally, I just wanted to showcase some of the modern desktop PWA APIs, like the File System Access API, File Handling APIs, and Browser APIs. But then in the age of AI, I also wanted to add some AI capabilities. So I can now open MDEdit. I can go to AI settings, and I have now different models like translation models, speech recognition models, and also text generation models. Like I have the Gemma 2B. I can create a new file. I can then use that and say, what is a GPU? And it will now run the model directly in the browser. And one pretty amazing thing is just how fast that is. Okay, so we see that to analyze the input tokens, it can do that at 123 tokens per second, and to generate output tokens, we are at 27 or around 30 tokens per second. So that's way faster than I could even read, and it's also faster than most of the cloud providers can stream their tokens back to us, and that is all happening directly on the device. I can also interact with it. For example, I can then say explain this like I'm 12. So I will add the instructions together with the context, and the LLM will then generate the text for me. Yep. There we go. Of course, I also have other models for things like translation, so I can translate that text now from English to German, and there I am using Transformers.js with a translation model, and everything you see is happening directly in this web application. So no data leaves the client, nothing is streamed from a server, it's all happening directly here. Now, having those, no, let's keep that open. Having those LLMs in the browser is pretty cool because we can do cool stuff, but most, or let's say all LLMs have one big problem. they are pretty bad at knowing whether they're telling the truth or not. If I ask the LLM, for example, who Albert Einstein is, I might get a quite reasonable result because information about Albert Einstein has already been in the training data, so it will give me a reasonable result. But if I ask the LLM if whether my health insurance plan covers glasses, then in the best case scenario, it will tell me that it has no idea about my health insurance plan. In the worst case, it will just make something up, it will just hallucinate. And to solve that, we have a concept called RAG, Retrieval Augmented Generation, where instead of just sending the question, we will also have the context. We will have a big context where we can then get the thing that, or the parts that are needed to answer the question, and we will send everything, the context together with the question, to the LLM, and then have a result from that. And most LLM cloud provider already have solutions, RAG solutions. But then again, do we really want to send sensitive information like our health insurance plan to some LLM cloud provider? I don't think so. And that's why I built another little project called Ask My PDF, which basically does RAG directly in the browser. Let's have a look here. So I can now open any PDF. Here I have the terms of service from Twitter. I can then say, can Twitter suspend my account? If so, for what reasons? And let's do that. I will get, not only I will get an answer, but I will also get the links to where, or the links to the sources that it needs to answer the question. So I can now click here, and I see that that's one of the sources it takes to provide the answer here as well. And the way it works is that first of all, I will parse the PDF, of course, and I will parse it sentence by sentence. I will then map all those sentences to a multidimensional vector space. We have seen a lot of RAG talks, so I won't go into detail, but basically I will have this model that maps the strings to this vector space. I will then store the string and the vector in a vector DB, because it's not actually a DB, it's just an array of strings and vectors. It's actually a gist. It's a very small TypeScript file that works as my vector DB. But then whenever I have a question, I will convert the question to the vector as well, and I will look for the most similar vector, so I know those sentences are important to answer that question. And I will then send those, nope, there we go. And I will send the context together with the question. So that's the whole prompt that the application generates and sends to Gemma 2B. I have some instructions. I do have the documents, all the information that it finds in the vector DB, and I do have my question. And one thing you can also see is that it only takes 81 milliseconds to parse the PDF. It takes 1.25 seconds to vectorize all the strings. It finds the 6 matches in 61 milliseconds, and it generates the answer under 10 seconds. So everything happens super fast directly on the device. And another pretty cool thing about RAG is that we can prevent it from hallucinating. I mean, if I ask Gemma 2, let's delete that. If I ask Gemma 2, why is water blue? There we go. It will write something. Water is transparent and colorless, blah, 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 blah. I mean, it sounds reasonable, but I have no idea. I don't know where it takes that information from. It is hallucination. It could be true, but maybe it's not. If I ask the same question in a RAG context, why is water blue? It will return none. So why will it return none? Well, if you go to the settings, we have our prompt template, and in the instruction part of our prompt templates, we say that if the document doesn't contain the facts to answer the question, return none. So I told it to be very specific. If it can't find the information, it should return none. I could also say return I don't know. And there we go. It says it doesn't know. So that's all running in the browser. You can try it out. And also, that's a very small document, and it's not really really interesting. I also tried it with bigger documents. There's, for example, this one here. It's basically a very big. I have it here. The idea it's a document where they talk about ways to improve the let's say the compilation of dynamically typed languages. So it's very long and very complex. But if we have that in RAG, we can now just ask what is the and tab dynamic tab, and can we do we can just ask questions about that document, and we will have the answer, and we also have the links to all the sources that it uses to answer the question. So now to sum the whole LLM part up, there is also a proposal for built-in AI. So Chrome is currently working on a set of APIs that would allow us to use AI models directly in the browser. Because right now, all my applications, they need to download their own models. I mean, here it was pretty fast because it was already downloaded and stored in the local storage. So you don't have to download them every time, but still each origin has to download their own models. With this new API, the idea was that Chrome and also Firefox and Safari, they would all provide an API to a model. So we could use this prompt API to interact with the models. There are a lot of pros and cons to that. I personally am quite skeptical about it because what I figured out is that different prompts work best with different models. So if I would use I did use the Mistral 7B before I switched to Gemma, and there I had different prompts that worked for this model. And when I can't be sure that every client is using the same model, that would then also mean that I would have to do some feature detection on which model is used, which prompt should I use for this or that model. So I don't think that's the final solution yet, but it's pretty cool that they are working on a solution, and they're also quite happy to get feedback. So if you're interested in that, you can go to developer.chrome.com to see all the documentation of how it works, and can also provide feedback. Yes?
Would it then still be on device?
Yeah, the question was if it's still is then on device, and yes, it is on the device because let's say Chrome will download Gemini Nano. I think at the moment they are using Gemini Nano, but it's downloaded once in the browser, and the browser will then run it under the hood in the end, and every client or every application could then use the same model. Right now, because we have each origin has their own storage, we can't share the models between origins, so therefore if we have this one model that is downloaded and controlled by Chrome, we can use this model, and it's still on the device, yeah. But in theory, it would also be possible if Firefox would say, hey, we don't want to have that on device, we would have the same API, but we would run it on some servers. I mean, in theory, it would be possible, but I don't think it makes sense because then they would have to pay all the server cost. So let's sum it up. AI in the browser, are we there yet? I mean, I've showed you some of the examples. Yes, we are. We are able to use pattern recognition. We are able to use LLMs, generative AI directly in the browser. But there's one small catch. As always, I am using the latest MacBook Pro with an M3 chip, and it works great on my device. I also have a Dell with an Intel i9 chip, which is a pretty decent chip as well. But there, it's almost 10 times slower than on the MacBook. And I mean, it's just not a very webby thing to require users to have specific hardware to use your application. So in the end, yes, it is possible, but yeah, it's just not yet there for all the devices. The future looks bright. I mean, I do think we will see smaller, more efficient models. We came from 70 billion, 150 billion parameter models, now down to 2 billion, 1.5 billion parameter models, like the Phi models, the Gemma models. Also, we will see affordable hardware. I mean, the MacBook Air has the M3 chip as well, and also Windows and Qualcomm, they are working on their Copilot Plus laptops where they have AI-optimized hardware. Maybe we'll have access to more advanced AI hardware like the TPU and the NPU with the WebNN API. And last but not least, I think it's very important that we should treat AI as a progressive enhancement. I mean, right now, everyone is just hyped up about AI and will create their AI editing platform, their AI whatever platform, and AI is basically the only thing that differentiates them from the rest. But I think once the dust settles, we will see more and more just normal applications that we can use and we can enhance it then with AI. I mean, if we take my Markdown editor as an example, it is a Markdown editor. You can edit Markdown files. Works on any device, in any browser, just like that. If you want to, if you are a power user and you use the tool for all your Markdown files and everything, then you can download the models, those 1.4 gigabytes for the Gemma 2, to have a better user experience. But it is a progressive enhancement. It's just you're not required to download the model to use the application. It is there if you want it, if you want to have this better user experience. The upside is pretty great as well. If we have AI in a web application, we don't need to install anything. We need to download the model maybe, yes, but in the end, we can just send the URL to our friends. They are able to open it, they're able to use it, they don't have to install anything. There's no Olama that you have to install. It's just there in the browser. It's highly interactive. As we've seen, we can do image recognition in 30 frames per second. And even if the models are faster on some cloud provider, we would still have the network. So we wouldn't be able to have real-time image detection or audio detection in the browser if you always had to go through some kind of network layer. Data stays on the client, so it's privacy preserving by default. We don't need to justify why we are sending which data, where it's stored, where it goes through. It will just stay on the client. It will never leave the client, so you don't have to justify anything. And it scales indefinitely. I mean, every one of you could go to my project, you could try it out, and I would not end up having a huge OpenAI bill because you bring your own processing power, right? There is not just one big cloud provider that takes all the requests. Everyone brings their own, and you can just play with it, and I don't really care about any bills. Yeah, so that was it from my side. Thank you so much for your attention. My slides are there behind the QR code. If you have any questions, I think we do have time for some questions as well. I will also be around for the rest of the conference, so if you want to talk about any AI-related or web AI-related stuff or anything else, just feel free to ask me. And also, I try to be active on Twitter and LinkedIn, so you can also connect there. Yeah, so thank you so much for your attention, and have a nice rest of the conference. Are there questions?
I would love to see this real-time audio transcription combined with your chat with PDF.
Yep.
Can you repeat the question for the recording?
Yeah. So you would like to see the real-time captions together with my PDF exam. So I could basically ask the LLM with like just ask the question in like talking, and then it would do that. It's not yet implemented, but I could do that. Yeah. Any other questions? Okay. So thanks so much for your time, and have a nice rest of the conference.